Hi everyone, so I thought I would do a bit of an explanation about how ignition coils work and how timing lights work, because there seems to be a bit of confusion about how you can use a timing light to check ignition timing. So, alright, we'll go to the basics. So an ignition coil is basically a transformer. It's got a turns ratio of, again, rough numbers, 100 to 1. Normally on the low voltage side here, you connect one side to 12 volts. The other side goes to an igniter, which goes to ground. That signal there comes from your ECU. And then this is the secondary side. That goes to your spark plug. I'm going to draw a very bad spark plug here. And then that would ideally be grounded at the head or rotor housing. Now, a lot of coils are actually not quite constructed like this, and this actually connects back to here, but we'll ignore that for the time being. Now, the way the ignition coil works is if you look at this voltage here, which is often called the coil negative, if that's 0 volts, we'll start off at 12 volts before we start the ignition pulse, because we've got 12 volts from here. Turn on the igniter, that goes down to about 0 volts. It's not exactly 0 volts, but close enough. And then after the dwell time, we turn off the transistor, and that makes a very big back EMF spike here, which goes up very, very high. It's limited by when the secondary starts to conduct, or when the protection diode inside the transistor starts to conduct. So that's probably 400 volts, 600 volts, something like that. Let's just call it 400 volts to make the maths easy. That becomes high enough to strike the arc and ionize the air inside the combustion chamber. So then it starts to conduct because it's plasma. And when that's, say, I don't know, 80 volts on the primary, which corresponds to about 8 kilovolts on the secondary, that will conduct for a while until the coil runs out of energy, and then it will no longer conduct and it'll be back at 12 volts there. So that 400 volts on the primary corresponds to about 40 kilovolts on the secondary. What it actually gets to, like I said, depends on the voltage that we need to ionize the air inside the chamber, which depends on the spark gap and the combustion pressure, and also the shape of the electrode to some extent. So this is the dwell time. So 3 milliseconds or 2 milliseconds or whatever, depending on which coil you have. That's the voltage at the coil negative. Now let's look at some currents. The primary current here starts off at 0. During the dwell time, it increases, and then it goes basically to 0 when the igniter switches off. That's what generates the big voltage there. The peak current there, again, depends on the coil and how hard you're driving it. Let's just call it 5 amps for the sake of argument. Now the secondary current starts off as 0, and it stays 0 throughout the dwell time because there's no current flowing here. There's no spark or anything like that. But once it starts conducting, the current will increase, and it will gradually die down there until there's no more energy left and the spark finishes. Now, because of the turns ratio, that being 100 to 1, again, give or take, secondary current there is only about 50 milliamps. Right, okay, so how does a timing light work? Well, you'd connect this. So there's a nice arrow here that says that's weighted to the spark plug. So you put this on the on that conductor there, and what that is it's a current transformer. So it's just a single turn there because it's just one wire going through the transformer core. And then inside here, there's a core, and you can see some of the ferrite material there with more turns on it. And I don't know what that actual ratio is. I've never pulled one of these apart. And that goes into the circuit that drives the timing light. So when it sees the secondary current here above a certain value, that's when it triggers the xenon strobe. Okay, so we're only looking for very small amounts of current to actually trigger the timing light, because it's looking at the secondary. So, and also because this only goes in one direction, this has a nice arrow on it, because if you turn it around and have the cord going through that way, then the current will be negative. So that's probably an important thing to note, is that currents going through one way, we'll just say for argument's sake, this with the arrow going that way is positive. So if the current goes that way, it's positive, and if it goes that way, it's negative. And if you've got two conductors going through, then they'll add together. If you've got the same current flowing in one conductor one way and then come back out again, then they cancel out and it becomes zero. Now, some manufacturers, Nissan's the only one that I can think of, provide this timing loop in the harness. Now, I'm not sure exactly where it connects to, but it's certainly fairly common that if you use your timing light on that loop, your timing will be off. And I'll just explain why. If it connects to the I'm not exactly sure how the SR and RB coils are constructed internally, but if it is like this, where you've got these three pins here on one end of the coil, and that's the bitey end, then you only need a small amount of capacitance between this primary and the secondary here to get a small amount of current here, which is all you need to trigger the coil. So if that happens, then the timing light is going to trigger sometime during the charging part. So let's just say it triggers at the start of the charging cycle, the start of the dwell time. That means that your timing is going to be, the light is going to flash 3 milliseconds before the actual ignition pulse. Well, sorry, before the spark. And depending on your RPM, that will translate into a decent amount of angle. So if you're at, say, 800 RPM, that works out to be 13.333 per second. So that works out to be 75 milliseconds per crank revolution. And so 3 milliseconds out of 75 is actually a decent amount. That's 1/25th. So 1/25th of 360 degrees is about 15 degrees. I think. Close to 15 degrees anyway. So if you set your timing using that loop, then because your time light is flashing 15 degrees earlier, if you set it so it's right, then your time will actually be 15 degrees retarded, which is not what you want, obviously. So some people have said that take the coil out, put a spark plug lead on it, use the timing light like that, and that will get you the correct result. And it does get the correct result, and that's the foolproof way to do it. But what you can also do is you can, I know this is the wrong plug, but just for the sake of illustration, if you put your timing light over the entire cable that goes into the back of the coil, that will have the same effect, because the same current is flowing through here that comes out here by Kirchhoff's current law. And I'll just draw it on a diagram to explain. If that's your coil like that, and that wire there comes out the back there, and there are your three terminals. and you put your current clamp around all of that, then any current flowing in through the primary that way is cancelled out by the current flowing back the other way. So the only current that you're measuring is actually the secondary current. The secondary current has to flow out through this plug because there's nowhere else for it to go, unless it goes through the mounting, like the body of the coil or something like that, but I've never seen a coil do that. So that's one type of coil. Another type of coil is, this one's actually an aftermarket coil for an RX-8. I'm not exactly sure how this is constructed internally. It has an internal igniter. So I would expect that that is connected back to the 12 volt supply. And the reason why I think it's connected to the 12 volt supply is that the factory harness has got a capacitor between the 12 volts and ground, which you don't need if it's going to ground. But anyway, that's the high voltage output here. This is the coil, this is the igniter that's built into the coil. So that box there is the coil, and these are the 3 pins on the back of it. So there's a few separate current paths here. There's the current path that drives the ignition transistor, which is 10, could be 50 milliamps. And through the transistor that comes out the emitter. So we've got that one going that way, that one going that way. The primary current, while the coil's charging, goes in that way, and then goes through there, and then also comes out that way. So both those current loops cancel out. And then the only one that you're left with, if you do clamp around the entire harness, is this secondary current, like that. So clamping all the wires together, where it goes into the coil, and you wouldn't bother doing that on an RX-8 because you actually have an ignition lead there, but the same principle applies to the coil and plug system. And for all the different situations where you've got a separate ground or 2 grounds or a power ground and a signal ground, it all works out the same way, because basically you've got a black box. The current can only go out that way or back this way. So if you do that, you should be right. Thank you.